My name is Isaac Yamahata. At the last Zen Summit Asia in Shanghai, I gave a presentation on PCI Express enhancement in QEMU. And in this presentation, I'd like to discuss my progress in that area. Of course, my eventual goal is to bring PCI Express features into Zen. But it requires several steps. So my first goal is to make QEMU PCI Express ready. So at the moment, my current focus is QEMU. Here is agenda. So my first question is why PCI Express? PCI Express is a successor of PCI technology, and it defines many more advanced functions than PCI. So, for example, it defines a PCI Express native hot plug and advanced error report or a virtual chain. It allocates bandwidth allocation for designated device. And it also defines a native standard power management. So it is very natural that users want to use those functionalities in virtualized environment. And this figure shows how PCI Express hot plug slots. There are two LEDs, power LED and attention LED. And there is a manually operated retention latch. It to hold us PCI Express card solidly. And there is a button for human operator to attention software, to get attention from software. PCI Express specification doesn't define how software handles the attention. And optionally, specification defines electromechanical lock. So for software to lock the slot to prevent human operators to remove card surprisingly. And this picture shows my eventual goal. Provide to show a virtual PCI Express bus to guests and allow PCI Express native pass-through to guests. And PCI Express detects if PCI Express detects error on a real device, catch the error in the DOM0. The error is PCI Express bus is owned by DOM0, so error is reported to DOM0. So capture the error in DOM0 and inject the error into the guest. Yes, but QEMU is not ready to express feature, so my first step is to make QEMU Express ready. Now QEMU emulated chipset is very old one, so I introduced a new chipset emulator. It is based on Q35. Integrated graphics is out of my scope, so someone said it should be called P35. And implement PCI Express native hot plug emulator and implement related PCI Express switch port emulator and add an interface to inject AER error into guest. Here is this table shows shows current status. I've implemented most of planned features. Only the remaining functions is AER and error injection. So next step is pushing those patches into QEMU upstream. And this table shows how hot plug function, how hot plug emulator is implemented. PCI Express native hot plug defines some functions are optional. So my choice is this. I did not emulate it. I did not implement a power controller and MR sensor. And I choose to implement electromechanical lock. But I'm not sure this choice is right or not. There is no technical reason not to implement, so it depends on usage model. If you want MRL sensor, or so please tell me so. Then let's see how to use and its usage, its example. To hot plug PCI Express device in QEMU, use PCI add and PCI del, or device add or device del. The command name is PCI, but eventually it calls bus specific callback function, so it eventually calls PCI Express hot plug callback. So although it's instead of its name, it can use for PCI Express hot plug. And to push the attention button, I introduce a new command. One interesting feature is we can insert a PCI device into PCI Express slot. In a real hardware case, the physical layer is different, so it is impossible to insert a PCI card into Express slot. But it doesn't matter in QEMU case. So we can insert a PCI device into Express slot. In fact, I'm testing inserting Express device into PCI Express slot. And to inject error, I introduced a new command. AR requires some information of error. It is error of type it's correctable or uncorrectable, and more detailed status, error status, and it records TLP packet header. PCI Express sends data as a packet, so when error occurred, its header is recorded in device. And optional TLP header prefix is optionally recorded. So now let's see how Linux sees that device. Here Linux reports mconfig area, and it says it recognizes mconfig and then Linux uses mmconfig to access PCI Express extended configuration area. And here is how Linux hot plug device recognize the Express hot plug double slot. I enabled PCI. I enabled debug option. So driver recognize hot plug double slot and reports how function is implemented. So let's see bus topology. So for now, QEMU only provides primary PCI bus. That is only it can have PCI bus 0, but with my patches, it can have many PCI bus. Actually, while I am testing, I added 64 slots. So now, we can see PCI Express capability. Here reports PCI Express hot pluggable slot, and it reports. So this is a PCI Express root port. And let's see how to hot plug occurs. I issued a PCI add command in QEMU monitor command line, and I inserted E1000 NIC. It is an emulated device. So hot pluggable device received the hot plug event and tried to activate E1000 device driver. To be honest, device driver reports hardware errors, but I haven't digged it. I haven't tracked it down why it reports error. And then once card is used, now you want to remove the card. So human operator push the attention button. So Linux deactivate the device driver. Again, E1000 driver reports hardware error. I suspect E1000 driver doesn't emulate it correctly, but I'm not sure. And then remove the card. Already device driver is already deactivated, so the hot plug driver only reports hot unplug event. And from proc interrupts, there was interrupts. So there were really activities in hot pluggable slot. Some comments on Linux. Linux doesn't use electromechanical lock. I'm not sure why. I suppose it just implemented. And the Linux AR driver doesn't record TLP header prefix. I suspect when they implemented the driver, they don't have real hardware. So there is no, it's not difficult to implement it. So I have a time I'd like to implement it. So let's see its implementation details. I choose to introduce new chipset. And so I have to keep all the chipset because QEMU can run very old legacy OSs like DOS or something like DOS extender. So I don't want to break those old softwares. So in practically, it is not possible to test all such legacy OSs. So old chipset and the new chipset must coexist. So I have to factor out chipset specific code and generic code. And I implemented PCI Express switch port emulator. There are three kinds of port: root port and upstream port and downstream port. they are very similar, but in detail they are slightly different. However, at first I had to clean up PCI breach code. In fact, guest firmware also have to be updated. And also I modified guest firmware. At first I modified box BIOS, but the QEMU project switched guest firmware from box BIOS to C BIOS, so I ported patches to C BIOS. In fact, C BIOS is much more easy to understand and easy to modify. So, and it only requires GCC. So BCC is not used. So it's very easy to handle C BIOS than box BIOS. So, and I also modify VGA BIOS. I didn't expect it at first. This QEMU hard-coded VBE base address, and it conflicts with MF config area. So I have to make it dynamic by paravirtualization. After I make the patch, I knew box project did it differently. So when pushing a patch, some discussion will be needed. And future work. Very soon I will complete error injection, and then I'll clean up. Once I clean up patches, I'll start pushing my patches into QEMU upstream. However, QEMU is very difficult to. The maintenance seems indifferent to those patches, so I need help to convince the maintainer. And once, middle term, I make QEMU Express ready. Then I'd like to address then itself. Then. So for that, QEMU DM have to be rebased to latest QEMU, and BIOS has to be changed from box BIOS based to C BIOS based. And I'd like to add PCI Express native pass-through and AR error injection. And some people would be interested in its schedule. QEMU next release plan is set for June 1st. And some proposed features are listed to this URL. And Q35 chipset and PCI Express is listed there, but it's just proposed list, so it's not. So I need help to upstream merge, and I have 10 minutes left. I'd like to discuss about some issues about further development. At this moment, there is no interesting PCI Express device which is emulated in QEMU. Port emulator, PCI Express port is not so interesting, so we cannot do Express specific interesting things. So it would be interesting to implement PCI Express native device emulator. Probably NIC is a good candidate. And for now, some AR function is defined as optional, so I didn't implement it, those optional functions. But probably, I think those functions are needed. So I'd like to implement them. And PCI Express native pass-through needs some considerations. At first, then QEMU must be rebased. In fact, my patches heavily depends on new QEMU framework. Recently, QEMU introduced QEMU device framework, and my patches depends on it. And so it is impractical to backport my patches to Zen QEMU. And the PCI Express native pass-through needs some considerations too. Enhancing configuration space access is not difficult, but some PCI Express extended capability requires some attention. Especially PCI bus is shared with several domains, so virtual channel or some error reporting must be virtualizing virtual channel or error reporting is not trivial. And PCI Express defines a device link, and device port the above the pass-through device can manipulate PCI Express link. So sometimes the link would be manipulated by guest. So such port should be a pass-through to the guest. So, but I haven't considered those issues much. And now then, PCI pass-through has much advanced multi-function support, but at the moment, QEMU only supports only function 0, so some consideration is needed. Especially, it is very difficult to make non-ARI function have ARI. And error injection is also some enhancement. Multiple error can occur in PCI Express bus topology. So error can be reported at the same time. So error injection also want to emulate it. So we want to inject multiple error at the same time. And capturing the error in the DOM0 is the issue. Current Linux AER driver only reports the error into the console. So there needs a way to capture the error. And when inject the error into the guest, some TLP header must be modified. And TLP header includes address or device ID that is bus device function. So those are virtualized, so those values must be converted. And its bus topology is also issue. In real hardware's PCI bus topology and virtual PCI Express bus topology can be different. So if error occurred in the middle of Express hierarchy, where to inject the error is not trivial. And error recovery is also needs consideration. as a error recovery, Linux may reset the bus. If Linux resets the bus, the reset is propagated down to device. So if each device is passed through to different domain, and error occurred in the middle of PCI bus topology hierarchy. This reset, how to handle this reset is not trivial. Now, this is a summary. Thank you for listening.
Actually, if no one else has questions, I have one. You chose to implement the Q35 chipset emulation to QEMU. You chose to implement the Q35
yes.
chipset. How did you choose exactly that chipset?
In fact, I choose that chipset. I have a real machine.